Hey guys, this is lesson 1.4, which is on velocity. So in my first video for calculus and vectors, I had talked about scalars and vectors. Speed is an example of a scalar because it has magnitude. Velocity is an example of a vector because it has magnitude and direction. So in this video about velocity, we're going to be calculating both magnitude and direction. Okay, so let's get into some examples. You'll notice that I write down all my solutions beforehand just because I don't want the videos to be like a million years long. And like I'll be skipping a lot of the steps for the math just because this is like grade 10 trigonometry. So I'm hoping that like your skills for trigonometry are pretty solid, but I want to develop or help you develop like conceptualization skills. And so a lot of the video will be based on how to draw the diagrams. I mean, if you can't draw the diagrams, you really can't do the simple math that follows. All right, so let's take a look at what this question looks like. A canoeist paddles 4 kilometers per hour in still water. So that means like without a current, this is just how fast the boat would be by itself. Crossing a river with a current of 8 kilometers per hour downstream. Okay, so here I have the stream and I also have a shore. Okay, so let's just draw the current first. So something like that. And I'm going to write down the magnitude, which was 8 kilometers per hour. We also have the canoeist. So maybe we'll just say she's traveling this way. Okay, and that was a magnitude of 4 kilometers per hour, like she's trying to get across the stream. And they do mention that she is heading across the river at 80 degrees to the shore with the current. So this diagram doesn't really warrant a lot of marks. First of all, it doesn't really make sense to have a number along a vector because a vector has direction and magnitude. So this isn't like a really great way to draw your diagram. This is just to put our thoughts down. If we were to draw like a vector diagram, we would be trying to find her ground speed and direction. So we want that diagram to reflect that. So a ground speed is what is the speed of her canoe relative to the ground? And what is the direction relative to the ground? So let me just see if I can kind of understand what's going on. Okay, let's take the ground and we will redraw it over here. And if she's going in this particular direction, okay, that's without a current, well, then the current, the current will probably push her down farther. So we're going to put this tip to tail and see what happens. So that makes sense that if she would normally be going in that particular direction, but then is knocked down via the current, then she should be going more in this general direction. We're going to call that her ground speed, but we know that this is the resultant, right? So I want the magnitude of the resultant, and let's fill in all the other information we know. So I have two let statements there where we have C that represents the canoeist's velocity. Okay, so the magnitude we already know is 4 kilometers per hour. And then the river, which is R, its velocity is going to be 8. Oh, they also told us the 80 degrees, right? Okay. So I can't really find the resultant unless, of course, I use some sort of trigonometry. Like I see the triangle, but you don't have an angle inside the triangle, and that's the problem. So if I just move this over, I can probably use the 80. Let's say that if I extended this line, that would have been 80 right here, right? Corresponding angles. Okay, so I want to find theta. Like, what's this? Well, this is a straight line, right? So shouldn't it be 180 minus that 80, and it'll give me what theta equals to? Okay, so let me just move that out of the way. Get rid of you. We know that this guy is 100. And bingo, we have a number inside the triangle, which means that if I have my side length of 4 and this side length of 8, I can do cosine law and find my resultant. Okay, so that is right here, and the resultant is 9.55 kilometers per hour. Okay, that's just the magnitude or the ground speed. I also need the direction, so I'm going to scroll back up again. And why don't we'll get rid of this. We already know what that equals to, 9.55. And I think I might want to move this. And we could just remember that that angle is 80. Okay, so if I want the direction, I'm going to get the direction relative to the shore because your resultant or your ground speed was already relative to the ground, and so your angle should also be relative to the ground. Okay, but in order to find that angle, I mean, that's outside the triangle, I'll have to work towards that corner of the triangle. So you probably want to find like alpha first, and then say 80 degrees minus alpha will give you, I don't know, we'll call it beta. Okay, so in order to find alpha, I do have an angle and its opposite side. Opposite side and angle, so I can probably do sine law and then take 80 minus whatever I get, and that'll be my beta. Okay, so here's all the work right here, and I got 24.41 degrees. Remember, I would expect all the approximation dots, all of the degree symbols, like everything is still like perfect communication marks, okay? So just because, you know, the concepts are more difficult doesn't mean we forget about that foundation for math. All right, the final answer, the Canoeist is traveling at 9.55 kilometers per hour. That is our magnitude. At 24.41 degrees, that's our direction to the shore. So it's important to say to the shore. So we have to say relative to what? This direction. What is it relative to? Both of those red and blue components will make a velocity. Okay, example number 2. A plane is heading due north, and so notice that I have 2 compass roses. You go north, east, southwest. Never eat sour watermelon. Okay, so let's draw the plane. We're going to say that the plane is P, and we're going from this due north, so straight up, all the way to here. And I don't know if you can see it, but there is an arrow at the top of this line. Okay, it has an airspeed of 400 kilometers per hour. Airspeed means like when it's not really disturbed by any wind. And so we have the magnitude of P, which is 400. Then all of a sudden it's blown off course, or I shouldn't say all of a sudden, it's probably always being blown off course by this wind. That wind is 100 kilometers per hour, so that's magnitude, and it's coming from the direction of northeast. So northeast is here. I'm going to draw this wind that's coming in from that direction. So it's going in this direction. Okay. Since they said northeast and they didn't mention a degrees, that means that this vector is actually completely in between, like equally in between the north and the east. That means that I can probably, let's use a different color, already tell you that that is 45 degrees because north to east is 90 degrees, so split it in half. All right, so what we're looking for is the ground velocity. Ground velocity is going to be the magnitude and the direction. But right now, I want to find my resultant, but they're not really tip to tail. So what we want to do is we want to draw them so that they are tip to tail. Okay, so there you go. This one's tip is at this one's tail. I'm going to make this one dotted so you know that we're no longer talking about that one. That was just before, and we're going to redraw it here. Okay, so this makes sense. If your plane was going this way and like wind decides to push up against it, it's not going to be going due north anymore. It's probably going to be going in this direction now. So that's going to be our resultant. All right, and that's what we're just going to try to find. So again, we have some information. This is our wind. Magnitude was 100. And we have no angle inside our triangle. Okay, so we got to find an angle inside of our triangle. That's not too hard actually, because this angle should be the same, 45 degrees, because it's opposite to the other 45 degrees. And since west and south are at a 90 degrees, then this should also be 45 degrees. Sorry, that's a 4, not a 9. Okay, so that's 45 degrees. Okay, now I have enough information. I have my side length of 100, I got my 45 degrees, and I got 400. So that's enough information to do cosine law. So I found out that the resultant, or the ground speed of the plane, is 336.8 kilometers per hour. Now you need a direction, because that's just the magnitude. Well, I don't see the ground, and so the way that we would describe the direction in this case is using the compass rose. And so what I would say is the plane would travel at this angle from the north towards the west. Okay, so how do we find that angle? Well, you already have this angle and the opposite side. You have this side, so you can find the opposite angle. You're just going to use sine law. Right? So right there, sine law. And I got 12.12 degrees. Let me just blow that up for you a little bit. This is the north, and it's going to travel towards the west 12.12 degrees. Okay, so we say that as north 12.12 degrees towards the west. And you're probably going to ask, well, do we have to do it in that order? I mean, since we know that this is 90 minus that 12.12 and we get 77.88 degrees, couldn't we also write it as west 77.8 degrees, 88 degrees, north? Well, yeah, I mean, like, technically both of those things are exactly the same. They both get you to the same place, but what we normally see generally is preferred is that the first letter is either a north or a south. We don't usually see it as a west or an east. And so this is not really preferred so much as this guy is. All right. So in conclusion, the ground velocity of the plane is a magnitude of 336.8 kilometers per hour with a direction of north 12.12 degrees west. Okay, so we've seen two easier examples. Let's throw a hard one at you. Okay, example number 3. A pilot needs to steer north 60 degrees west to reach an airport. So the thing is, when it says he needs to steer, it doesn't mean that that's actually where he's steering. It means that that's probably what's going to happen when he's blown off course. So what I'm going to do is I'm going to draw, let's say, a dotted, because I want to show you that that's the resultant. I'm going to draw it maybe like somewhere here. We'll say that's going to be my resultant, and let's give it a color. I don't know if you've noticed, but I like colors. Okay, so this is going to be my resultant. All right, and it's going to be 60 degrees north to west. Okay, so his flying speed in still air is 300 kilometers per hour. So this is not where he's actually flying right now. He's flying, and I'm going to make him fly this way. Okay, I'm going to tell you why in a sec. So let's pretend that this is the actual plane, and we're going to represent it by P vector. And so we already know what the magnitude is. P equals to 300. The reason why I pointed it towards the other compass rose is then to signify the wind, because wind is starting to blow at this plane at a south 80 degree west direction. And so here's my south and west, and that's why I decided to draw the compass rose in the first place, is to show that there's going to be wind that comes in this direction. Okay, so it's coming from the south, southwest, sorry. and it's south 80 degrees west. All right. Now, we have like all the vectors, but again, this doesn't really warrant any marks because, or not very many marks, because you really want to show that triangle that creates the resultant vector from the other two vectors adding together. And so let's copy this vector, and I'm not going to extend it, I'll just move that one that way. Okay, so now we have our triangle. This one I'm just going to put dotted so that you don't really pay attention to it too much anymore. Okay, and there's my triangle. I have, starting from here, the actual plane being thrown off course, and so it will go this way. All right, I think they also gave us the wind, didn't they? The magnitude of the wind. So this guy right here, wind is going to be, what was it, 85 kilometers per hour. Okay, so from all of that, we have the airport that it's trying to reach right here. We'll just call that the airport. And let's see what they're asking for. So A, at what heading should the pilot steer to maintain his desired location? So what you want to say is he's actually not wanting to steer the 60, but let me just extend this. So that's the north line. You want to find this because he's going to steer this way and then get blown off course to then land at the airport. Okay, so you don't want the 60, you want that entire angle. So this guy, and we'll just call that gamma because I think we're probably going to have to find this guy, which I'm just going to call alpha. Okay, I'm going to make that blue because I want all the colors to coordinate just in case you decide to look at this later. Okay, no angles inside my triangle. Bummer. Okay, so we're going to have to use some skills. Okay, so that's our north, south, east, west. North, east, southwest, sorry. If this one is 80 right here, then that means that this guy will also be 80. Okay, if this is 60 right here and it looks like I can make a Z, which is alternating angles, well then that means that this is also 60. So I have this entire angle of 140. Booyah, I got an angle inside my triangle. Woo! Okay. All right, so I'm going to show you the solution. We have the 140 in green. Then we can easily find alpha because we have opposites. We can do sine law, and then we would just add alpha, which is 10.49 to the 60, and we'll get gamma. Okay, so that is the answer for A. The pilot's going to have to steer north 70.49 degrees towards the west. Okay, that was A. Now, I'm very sorry, but I'm going to have to erase a lot of this so that I can do the next one without having to redraw the diagram. Okay, so let's erase a lot of my scribbles. You know what, why don't we put you right there? Okay. Let's get rid of you, and get rid of all of you. Okay, but we will grab B and we'll bring it up. See, now I don't have to draw my redraw my diagram. And my solution is right here. Perfect. Okay, so what does B ask for? What is his ground speed? Well, ground speed was, tell me what the resultant is. Right, so let me just underline that in orange. Basically, figure out what this equals to. What's that? Okay, I think we have enough information to kind of go there now. Like, we could probably set up a sine law somehow. If we do this guy and this side length, and oh, I'm going to have to find this angle. Okay, let's give that a name. We will call it, I used alpha, beta. Okay, so that's this angle right here. All right, to find beta, couldn't we just do 180 minus the green 140 minus the blue 10.49 degrees, and then we would get our purple, okay, 29.51 degrees, and then we can use that to find our resultant of 229.89 kilometers per hour. Okay, so that is the ground speed. I hope that this entire video has kind of solidified how to draw the resultant vector in a triangle and then use a lot of the trig in order to calculate different things. Okay, so we only have one lesson left for this first unit. Thanks for sticking with me.